Welcome back to the Explainer series, everyone. So previously, we laid the groundwork, right? We looked at transfer functions, poles, zeros, all that good stuff. But let's be real, math on a page is kind of just math. Today, we're taking those abstract mathematical concepts and setting the stage to translate them into actual physical reality. Where systems actually move, vibrate, and operate in the real world.
Think about this for a second. Can a single mathematical function really predict if a complex engineering system is going to safely operate or if it'll just violently spiral out of control? It's an intense question, but honestly, that is the incredible power of the transfer function. Before we can fully break down exactly how it does this, we need to understand the two distinct ways a physical system actually behaves. Okay, let's dive right into this roadmap. Think of the transfer function, that g of p, or maybe you call it g of s, as the literal DNA of our system. And just like DNA, it dictates traits. Here, it basically splits into two essential defining traits. On one side, we've got system survival, which we call BIBO stability. And on the other, we have the system's personality, its frequency response. Every physical, continuous time LTI system you're ever going to design or analyze, it's going to be judged by these two branching paths. So let's start with part one, system survival, defining BIBO stability. To actually guarantee survival mathematically, we use this concept called BIBO stability. BIBO simply stands for bounded input, bounded output. Honestly, it's a fundamental rule of engagement for any kind of safe system design. Now, what does this actually mean in practice? Imagine you have strict upper and lower limits. Let's call them bounds m and n. They're just finite constants. Translating the math into plain English, a system is BIBO stable if, and literally only if, every single finite bounded input you feed into it strictly results in a finite bounded output. If you give your system a constrained signal that never exceeds your input limit, well, the system absolutely must give you a response that never exceeds its output limit. If the output suddenly shoots off to infinity, yeah, no way. You've got an unstable, violently self-destructing system on your hands. Or, at best, a very expensive paperweight. This is our global macro-level check for system survival. Moving right along to part two, the system's personality, frequency response. Okay, so to figure out a system's personality, we study its frequency response. The core idea here is elegantly simple. When we feed a steady-state LTI system a sinusoidal input, it outputs another sinusoid. And here's the kicker. It's the exact same frequency. But the system adds its own unique twist to it. It actually alters the signal based entirely on its own internal characteristics. That unique twist the system applies, it comes in two distinct flavors, magnitude and phase. Magnitude refers to gain or attenuation. Basically, does the system make the input wave taller or shorter? Phase shift, on the other hand, refers to the time lag or lead. Does the system delay the wave or sort of push it forward in time? These two parameters completely define the steady-state personality of our system, but how do we actually find them mathematically? This is where the math behind the magic comes in. We take our transfer function, g of p, and we evaluate it strictly on the imaginary axis of the complex plane. By simply replacing the complex variable p with j omega, we suddenly have this incredibly powerful tool. It reveals exactly how the system modifies the input at any given frequency. The magnitude of g of j omega gives us our amplitude ratio, and the angle gives us our phase shift. By sweeping through different frequencies, different omegas, right, we can see exactly how the system changes the amplitude and phase of literally any sinusoidal input we throw at it. Which brings us to part three, the secret architects, the power of poles. All right, here is where it all connects. Pole locations dictate absolutely everything. If your system's poles are located in the left half of the complex plane, you are good to go. It's BIBO stable with a nice, smooth roll-off. But if even a single pole slips into the right half plane, the gain grows unbounded and the system literally breaks apart. And right in the middle, poles near the imaginary axis create a massive resonant peak. Actually, fun fact, this exact type of resonance is what caused the infamous collapse of the Tacoma Narrows Bridge. It's wild. The poles truly are the secret architects of both survival and personality. Let's do a really quick recap of what we've covered in today's explainer. First, BIBO stability means a bounded input strictly gives a bounded output. That's your global safety check. Second, we find a system's frequency response by evaluating our transfer function on the imaginary axis, which shows us how it changes amplitude and phase. And finally, the locations of the system's poles secretly control both of these outcomes. But hey, this is just the beginning of our journey. In our next explainer, we're going to dive much deeper into analyzing these frequency responses using bode plots. I want to leave you with this final thought today, though. Pole locations dictate both stability and behavior. They are quite literally the master dials of your system. So where are you going to place yours in your next design? If you found this explainer helpful, definitely share it. And drop your thoughts or questions down below. Let us know what parts you'd like us to explore in more detail next. Until then, keep learning and designing smart.